Hello, everyone, and welcome. I'm Brian Tristan Williams, and welcome to today's Elector webinar called Spurious Emissions Testing for Amateur Radio Transmitters. And in today's session, we're looking at RF measurement in the real world. That's how spurious emissions testing should be done, what ETSI EN 301783-1 requires, and that is quite a mouthful, but I will say that ETSI stands for European Telecommunication Standard Institute, and why measurements that look perfectly plausible on your spectrum analyzer can still fail under scrutiny. So we're not going to go too heavily into broad theory, heavily EMC, but rather on practical measurement technique, which you would expect from Sebastian from Baltic Lab. We're talking setup, bandwidth, correction factors, analyzer settings, and the details that decide whether the result is accurate, repeatable, and defensible. Now, I will talk about our giveaway for our show. As always, we have a giveaway here, and today it is the Tiny SA Ultra Plus ZS407 Spectrum Analyzer, and it's a compact handheld instrument that's a very good fit for today's topic. It gives users a practical way to explore signals, analyzer settings, frequency spans, and the kinds of measurement pitfalls we'll be talking about today. So later in the show, we'll give you the code word to enter as always. And then our sponsor, I'd like to tell you about Elector Academy Pro. Elector Academy Pro is Elector's training and learning platform for engineers, developers, educators, and technical teams. It brings together practical electronics courses, webinars, books, bundles, and hands-on learning material built around real engineering tools and projects. So today's €50 webinar is brought to you free thanks to Elector Academy Pro. And you can find it at academypro.elector.com. Now, it's my pleasure to introduce today's webinar presenter, Sebastian Westerholt from Baltic Lab. Sebastian, how are you doing?
Pretty good. How about yourself?
I'm great, thanks. I see there's a contrast in lighting between us, but I like your little Batman lair that you've got going on there. I'm jealous. It does look like you have... Yeah, well, you're going into summer, I'm going into winter. I think the tan appearance is appropriate. For our audience, Sebastian works with practical RF, EMC, and test and measurement topics. His approach focuses on correct measurement technique, standards-aware testing, and the real-world mistakes that can creep into measurements that otherwise look reasonable. Let me show you some of Sebastian's web pages. You will see the links in his presentation, but you can find Sebastian on Baltic Lab, baltic-lab.com. And as well, if you're German, baltic-labor.de, I guess. I think in German you say minus, baltic-labor.de. And then also we've got his YouTube channel. Just look up Baltic Lab on YouTube and you'll find Sebastian there. So let's tell you a bit about Sebastian. He works with practical RF, EMC, and test and measurement topics. His approach focuses on correct measurement technique, standards-aware testing, and the real-world mistakes that can creep into measurements that otherwise look reasonable. I've already said that, yeah. That's the heart of today's session, however, and as a guy who was very comfortable with digital electronics myself, I think Sebastian is an absolute genius for what he knows about RF and analog. It's way, way outside of my wheelhouse, and it's going to be a fascinating session today. A lot of people have access to spectrum analyzers now. That's a good thing. But owning an analyzer and making a valid RF measurement are not the same thing. So today we'll be looking at how spurious emissions testing for amateur radio transmitters should be performed under that ETSI specification. I won't read the whole number. You'll see it enough today. And why simply looking for peaks on the screen is not enough. So we'll be covering all of that in relation to amateur radio transmissions, how to choose the correct resolution bandwidth, how attenuators, cables, and correction factors affect the result, and how spectrum analyzer settings can distort or invalidate measurements. So you need to make your RF measurements accurate, repeatable, and defensible. Sebastian's the guy for it. If you've ever connected something to a spectrum analyzer, seen a nice, clean-looking trace, and wondered whether that was really enough, today's webinar should be useful. Audience, thank you for joining us. I see Frank de Hart was first in the room, as usual. And hello to everyone else from around the world. You are here to ask questions and to learn. So while we're learning, please drop your questions in the comments. And as it's a webinar format, we'll take questions after the presentation, just after we give you the giveaway code for today's giveaway. So, Sebastian, over to you.
Well, thanks for the double introduction. I'm gonna correct you in one thing. Yes, Brian always says questions at the end, but if you post them in the chat, I have enough ADHD that I will usually respond immediately, because if you ask me at the end, I will have forgotten what I was talking about. Just saying. But anything I forget, we'll get to in the end.
Okay,
the other
well,
thing
at least
I'd like
you can multitask. That is an issue for me.
for an hour, it's okay. After that, not so much. And the other thing, if you say, okay, I'm just here for the show, but I don't really care about spurious emissions, doesn't matter. Any measurements with spectrum analyzers will have these issues that I show. So even if you don't care about amateur radio, if you don't care about spurious emission measurement, it's still going to be very interesting, because most people measure completely wrong with their spectrum analyzers. And I see plenty of YouTube videos where people show measurements that have absolutely no meaning, as you will see in a second. Yes, the baseline for this webinar is going to be the ETSI EN 301781-1 long term, which doesn't matter. Let's start with what are spurious emissions. And this is the definition found on Wikipedia, which itself cites it just from the 47 CFR something rules of the FCC in the United States, which can be summarized as any signal emitted from a device other than the intended. Any device, I have a radio right here, like this one, if you set it to any frequency, it will also transmit on multiples
Show us
of
the radio
them.
again, please.
Yes.
Let's have you full screen for that.
Wait, I have to hide my face because of auto tracking. It doesn't work. There.
Product showcase mode. Nice.
Yes, I have it, but not enabled. And here's just a graphic for that. If we have the intended frequency, I don't know why I picked 30 megahertz, but sure, why not? We also have some emission at twice that frequency and 3 times that frequency, and so on. It goes quite high. This ETSI rule only concerns itself up to the 10th harmonic. This is already an idealistic scenario, because usually there's also intermodulation products. These are purely the harmonics. Anything that appears as non-integer multiple of these frequencies is just going to be spurious emissions. And I promise I will get into the practical stuff very quickly, but the theory is important. The first thing you might ask, what frequency do I have to test on? Like the device I just shown goes from 136 to 174 megahertz. Do you have to test on every frequency? No, not at all. Generally, the rules are on the screen, but you can summarize them all in the middle of the band. There's some exceptions where you don't have to test them all, but if you test exactly in the middle of the band, you're golden. Now you have to be careful, because the band allocations change a little bit around the world, but within Europe, they should be fairly, well, they are pretty uniform. One thing, and that's the first thing that I haven't seen a single video or article cover, is the power supply. All of these radios, I wish I know how to get the battery off, but nowadays I need a screwdriver for them. Not gonna do that. You may not power it off battery at all. You have to use a power supply, and there are some rules regarding the impedance, so that it doesn't, if it would have a high impedance, the power source, obviously the power level would drop, and with the battery it could be higher, and your spurious responses could be worse. If it has a battery, it technically has to be removed. I'm not doing that. Nowadays, they all have a USB-C in the back of the battery. So I just connect a power supply with fairly low impedance to that USB-C input and make sure that the battery is full. Is this completely standard compliant? No. Does it matter? No. I've also compared that before, but I'm just mentioning the rules. The next thing I've never seen, and this is really different from the United States. In the United States, the rules that the ARRL uses in the lab is to use unmodulated signals. In Europe, you should use modulation like that simulates voice and the entire spectrum that you would usually carry, but only if it's a non-constant envelope modulation. So AM, for instance, a SSB, the envelope of the signal changes by the modulation, and the exact characteristics of these modulation signals is shown here. Now, I just said if it's a constant envelope signal, you do not need an external modulation source. FM is shown. FM is a constant envelope modulation. It's optional. You do not have to use it. But for everything else, if you ever see anyone show AM or SSB without a proper test signal, it's wrong. Then the test load, which is called artificial antenna in the standard. Let me jump a step back. I didn't put that in the slides, but usually these newer radios, you can just unscrew the antenna. It's an SMA connector, and you can connect to it. If you cannot do that, you have a problem. It is permissible, and this is usually how devices are designed, to open the device and connect directly to where the antenna connection is, but there must be a test point specifically for that purpose, else you cannot do that. Should you come in a situation, wait, do I have one here? No, too bad. I thought this one was a fixed antenna. Should you be in a situation where you have a fixed antenna on there, you will have to do a radiated measurement, which I'm not gonna talk much about, but you'll need an anechoic chamber, an open area test site, and a calibrated antenna. You will not be able to hook up directly to the antenna connector. Just mentioning that. Then obviously the dummy load that you're going to use has to have a 50 ohm match if the radio is 50 ohms, which it usually is. That needs to be stable over the entire bandwidth. And of course, it needs to be able to handle the power. The power handling, I often see that people measure a device that puts out up to 100 watts of power and have a 100-watt dummy load. It's not a good idea because that's a maximum limit, and the dummy load will heat up. And while it heats up, it will, excuse me, it will, of course, change its characteristics. So make sure you have plenty of headroom. Like for these less than 10-watt transmitters, I always use a 100-watt dummy load. Yes, there is that dummy load. Do I have a pointer? Can you see my arrow from the mouse?
Yes.
Good. Here is the big 100-watt 30 dB attenuator. It's rated to 3 gigahertz. Doesn't cost much. Yes, there it is. You have to, of course, verify whether or not it actually is 30 decibels. And that's the next thing I often see. People buy stuff and then believe that a cheap 30 decibel attenuator will have exactly 30.000 decibels, and that over the entire frequency range. That is not the case. Here is an insertion profile, insertion loss profile of that attenuator I've just shown. Let's start with this marker here. This one is at around 1.65 gigahertz. It drops to minus 37 dBm insertion loss. That is 7 decibels more at this location than it should be. Obviously, measurements at this location may be wrong. Well, not may be wrong, will be wrong. So the question is this a poor quality attenuator? No, it's not. On to mistake number 2. End connections should be torqued, and most people don't do that. Even if you have monkey wrench hands, you are not going to tighten them to spec. You can over tighten them, they'll break eventually, but just this is measured beforehand, torqued, and this is measured afterwards. And they were really hand tight. I did not overdo it just for this video. And for repeatability, be sure that you torque your connections. Especially in hobbyist labs, I don't see that, but even at universities and semi-professional labs, at least for end connectors, I rarely see anyone use a torque wrench. Now, what you also see here, this dummy load is rated for up to 3 gigahertz. And if you look at my marker there, up to 4.5 gigahertz and a little bit above, it is more than usable. So this is a really good attenuator. There are the smaller ones. I might get into later why we need so much attenuation, because 30 decibels might in theory be enough, but it really isn't. And this is also an excellent attenuator, which you should always verify. You see it's really flat. Wait, where's my mouse arrow there? This is up to 8.5 gigahertz up here. And I'm going to say 4.5, 5 gigahertz. It's very well. I mean, there's some ripple starting to appear, but you can correct that easily, which we will also get to a little later. Next source of error, which we all have drawers full of some questionable adapters. The cheapest stuff that you found on Amazon and eBay, yes, I know proper ones are expensive, but don't use them. Those are my two drawers of, well, you can use them, but you shouldn't for anything meaningful. And we all have a drawer like that. Get yourself some proper adapters. This is an example there from TechBox. Yes, they cost a bit more. This entire set cost around, I think, 200 euros. But these are good for repeatability. You will need that. You have accurate insertion losses on the data sheet that you will later on need to correct. And the most important thing is that it's also constant over a broad frequency range. If you just measure at one location, nobody guarantees you that the same behavior is present at, I don't know, 4 or 5 gigahertz. So please do that, or at least verify the cheap stuff you got on Amazon. It's bad advice, but I've done it. If there's a 10-pack of some adapters for a few bucks on Amazon, order 100 of them and just measure them out and pick the best. And that's still cheaper than professional kits. So with that said, that's in theory everything we need to measure, right? We have the radio right here. We have the big attenuator. We have a cable, another attenuator going right into the spectrum analyzer. One thing that's missing is, what are we testing against? What are the limits? I'm not going much into that, except that they depend on power under ETSI rules. Although if you do the math here, this equation 43 plus 10 log peak envelope power, you will find that only above 100 and something watts, this will actually be stricter than this minus 50 dBc. So you can usually assume this. For us here, this is a VHF UHF radio. Minus 70 dBc is a good reference. dBc, if you've never heard it, that's decibels in regards to the carrier. So the carrier is the reference, which I will explain later on a precise measurement. And this is a funny thing that people, I've never seen that being mentioned anywhere, but it's in the rules. You don't just test for spurious emissions while transmitting, but also while the radio is in receive mode. And I've seen there's plenty of amateur radio operators in the comment sections, and depending on your age, you might remember very simple transceivers from the 40s, 50s. When somebody would tune their radio, the local oscillator would feed through, and you can actually hear that, especially when you were in CW mode, that somebody's local oscillator was running on that frequency. And that's important and often missed. You also need to check in transmit mode. Right away, I can say that really doesn't matter much on VHF and UHF radios. On modern radios, not at all. But if you have an old tube set or something like that, for nostalgia reasons, you should check that. Another thing that's mentioned in the rules, and that will cause issues later, and that's the issue that most measurements with common spectrum analyzers fail under, but I'll get into that. It's the resolution bandwidth, which is essentially the bandwidth of the input filter before the detector in the spectrum analyzer. For the range that I have here, it's VHF through UHF. The resolution bandwidth is 100 kilohertz. If you want to be technical, this relates to the harmonic itself, not to the fundamental frequency. So all harmonics above 1 gigahertz would have to be checked with a resolution bandwidth of 1 megahertz. I personally am not doing that, at least not with narrowband FM signals. I stick with 100 kilohertz throughout the entire band. I've done comparison measurements, and I've never noticed a relevant difference. So back to the test setup, you see there's some peaks there, and I'm thinking if I'm gonna leave a small break here and ask the comments to give their opinion. I think I'm gonna do that. Remember, the radio is tuned to 145 megahertz, the center of the 2-meter amateur radio band here in Germany. And the frequency is accurate. And the Rigel spectrum analyzer is not cheap. That RSA 6K is, I wish it would only be 6K, it's closer to 10K in money. And if you look at the frequency, the fundamental is given as 143.75 megahertz. So something went wrong here. And this is a very common mistake. It's an easy mistake, but I'm going to claim it's fairly unknown. And I see Brian joined, so we're gonna use a small gap here, maybe 30 seconds. I want to ask the audience if you can imagine why the frequency measurement is off. And I'm going to give you the hint, it has nothing to do with the frequency accuracy of the transmitter or the spectrum analyzer. Even if I would GPS lock that, it would still have that mistake. And I did give you the span and the frequency settings here so that you can think. Brian, do you have a suspicion?
I do not, and I don't feel too bad because the chat is suspiciously quiet as well.
That's what I expected. It's the most common mistake on any spectrum analyzer measurement, but I wanted to give them maybe 20 seconds to see if anyone has an idea. It's a really mean mistake, I have to say, that all spectrum analyzers intrinsically have.
Ari has a suggestion.
Wide resolution bandwidth. It is exactly the 100 kilohertz it's supposed to be, but resolution bandwidth is a good thing. TX-RX offset, no. Alias, no. Timing problem, no. Resolution bandwidth is a good direction.
Okay, so back to Ari's hint. And I must say, I will jump in here just to point out that we have a lot of hammers here with their handles.
Yes, so I've seen that.
Exactly the audience. I just wanted to save these to put them up. You guys can seek each other out on the 50 ohm antennas and the airwaves. We got the answer in the chat. Christopher nailed it. Christopher, he says it's the spectrum analyzer synthesizer. Tell us about that. Yes. Okay, let me move on to the next slide. What people forget, and I should have probably put some descriptions on this image, but sure, why not? I am here. Like, actually, let's go back. Right now, it's set to a span of 1.4 gigahertz. That means this from here to here is 1.4 gigahertz. The resolution bandwidth is 100 kilohertz. This spectrum analyzer in particular has 801 points between here and there. That looks something like this. So the distance from each one of those humps, those are the sampling points, is going to be 100 kilohertz distance. Any signals in between are going to fall outside of it and are essentially invisible. Now you're going to ask, well, but it wasn't invisible, it just showed at the wrong frequency. Yes, because the 3 dB bandwidth of this Gaussian-shaped filter is the frequency given. So the 3 dB bandwidth is 100 kilohertz. Well, that doesn't mean that a signal that's outside of that bound doesn't come through. So if somebody would do the math, the 143.7 something megahertz would be this peak of where the spectrum analyzer thinks it is, and the signal is in our case actually above. So we're getting a false frequency reading and a false amplitude reading. Both are wrong, and this is the number one thing. If you take away one thing from this entire talk, it's this, because you will see it everywhere after that. People use the largest span that they can get because they want to see everything at once, and they never think about the points. And if you have some understanding about that, you can make really good measurements. Now, this rule here, resolution bandwidth times 2 as distance, is from the EMC world. It's not in the ETSI standard.
but it's something that I do. For instance, with the 801 points of the Rigel RSA, if you assume 100 kilohertz resolution bandwidth, that would give you 40 was that true? Yes, 40.5 megahertz that you can use as span, which I'm doing here. See here, the span is 40.5 megahertz. I still have 100 kilohertz resolution bandwidth. My center frequency is 145 megahertz, and all of a sudden, the frequency reading is correct. And this issue will really come to bite you because it changes with every spectrum analyzer, obviously. Brian, if you can put me up for a second so that I can try to do showcase here.
Put you on full screen.
Yes, and I have to hide my face again, right? Yeah. That's the Tiny SA Ultra that's going to be given away at the end of the show. And that one, for instance, has, I think, 450 points. So you can do the same measurements with that, but you will have to use a completely different span, around 22.5 megahertz, to get results. And we will get to that in a bit too. Now, the really annoying part about it is, as you can see here, now I have to cycle through and step every harmonic. And this is exactly what I had to do here in this case. This is the fundamental, and here we have 435 megahertz, which is the third harmonic. And then we have the fourth harmonic at 500 and something megahertz. So you have to step through every single one and note it down. And there's still a major amplitude, not defect, error in there that we haven't addressed yet. Right, and that's the next thing in the slide. The next thing we haven't addressed yet, here we see we have 145 megahertz. The frequency is correct now. How reliable is the amplitude? Well, at this point, not at all. I did a gain of 50 decibels, which is correct. We go back. I have 30 decibels here, and I have 20 decibels here. That's the sum of both attenuators. Problem with that is, as we've seen earlier, it's frequency dependent. The attenuation of the cable is also frequency dependent, so I can't just say it's 50 decibels. It changes over frequency. Now, all modern spectrum analyzers, although I'm not sure about the Tiny SA, I've just gotten it last week and I haven't played much with it, but you can enter correction factors, which of course requires you to measure them first. So you have to make a through measurement with your cable, with your attenuators, and anything you might use, like the adapters. And then you have to enter those correction factors either manually, which the Rigel RSA can do. Here you see them for the cable. I don't know how well that shows on the screen. It's like 1.26 decibels at 6 gigahertz. So you're not off by much, but sometimes that matters. And here is the, I think it's the 30 dB attenuator. I have it actually in 10 megahertz steps, and the spectrum analyzer interpolates in between. And you see there's sometimes 2 digits behind the decimal, which is really not much deviation, but it's still deviation that sums up afterwards. Now, that's something you can do by hand. If you have the Tiny SA Ultra, for instance, just do it by hand. I've done that. I actually did not want to include the Tiny SA in this talk, but then my ADHD kicked in earlier, and I, of course, had to bring it in. We'll get to that. So those are the two primary sources of frequency error and amplitude error. If you get those two things right, your measurements are better than most measurements you'll ever see around you, which is kind of scary. Now, more expensive devices like this Rigel RSA 6085, they have an option, a software option, where they do this work of measuring every harmonic individually for you. So the only steps it takes is the harmonics. You need to be careful with that because it really just captures harmonics. We talked about spurious emissions also including any other emissions in between. So you really have to step through the entire frequency band. And how high do you have to go? Up to the 10th harmonic. So at 145 megahertz, you will have to go up to 1.45 gigahertz. Keep that in mind. Annoying if you don't have an option. Easy, like here, if you have an option that automatically averages, corrects errors, and applies correction factors. Ari says that the Tiny SA Ultra has harmonic scan which prevents this problem. Okay, cool. I suspected it, but now we know. So apparently the TinySA also has a harmonic scan. That is really good to know. Thanks for the input. I really just got it last week, and the sole reason I got it because I know that topic comes up during webinars. We had that before. And so the same company, Elishop, that is partnered with Electra to give it away, sent me one, but just last week, and I haven't had enough time to play with it yet. But that is good to know.
Nice. And it's great coincidence that we're giving away the TinySA Ultra Plus, the ZS407. Ari, do you have one? We'll continue and wait for Ari's response.
Yes, I saw that was going to be the giveaway, and I also saw that Elishop was the partner. So we are in exchange. They are a sponsor of the blog, and I said, listen, they are going to ask me how well does this device work for this, and so they immediately sent me one, so I can finally also talk about the TinySA, which we will in a second. Here is the measurement, by the way, with the harmonics function of the Rigel RSA 6085. So what you see down here is the frequency, the harmonic number, and then the amplitude for the fundamental absolute in dBm, and then the rest is in dBc. And this thing fails horribly, by the way, like the third harmonic. Wasn't there one that was worse? No, it was a different radio. Minus 70 dBc is kind of our target, and we're far away from that. I mean, even at 1.45 gigahertz, although I'll admittedly say this is really mostly just noise back here, but it doesn't really matter. It's also a question I often get in this regard. If my noise floor is not low enough, does this matter? Well, depends in what direction. You really only need to cover the minus 70 dBc, and that is covered here, and that's fine. Like, I mean, you don't need to see all harmonics. You just need to be sure that they are below the limit. And if they're invisible beyond that, it doesn't matter. The UV32, that's the one that I have right here. And that was the one I was going to use initially for this webinar. And the reason I did not use it is because it actually passes. It passes so well. The most impressive part about it is that the 2-meter harmonics, the third harmonic, which falls right into the 70 centimeter band, usually that is an issue, which we see here also. Now it's very strong, the third harmonic. It's very well suppressed, or the DM32UV. Very impressive radio. I think I even posted a short about that somewhere on my channel. Check it out and see. I don't remember, because what I have actually done and what I have planned is usually two different things. Wrong direction. Yeah, we already dove into that, but sure, let's make that official. Now, how does an expensive analyzer like the RSA 6085 compare with a TinySA? Or let's frame this question the other way around. Can you use a TinySA for measurements like this? The answer is yes, but it's more difficult and tedious. But there's another issue, and this is a typical TinySA issue. Of course, this incorporates the original mistake of the entire span again. Unfortunately, I can't read the span here, but I think it was up to 1.4 gigahertz. I'm capturing a very large span, which has our issue with the points again. But let's ignore that for now. There's a bunch of garbage in there, especially those clusters here. You can see that there's multiple peaks very close to each other, and it has the same amount of attenuators in front of it and even 10 dB of internal attenuation. What's happening here is, and this is just an old graphic from me about intermodulation products, anytime you push more than one signal in any nonlinear system, be it an amplifier, a mixer, or anything of the like, all those signals are going to mix with each other. Now you might say, well, I'm only putting a 145 megahertz signal into the device. You're not. You're pushing that signal and its harmonics into the device. They all mix with each other. And this disaster here is only graphed up to the third order intermodulation products. There's a whole lot more of those. And this is what you see on the TinySA if it's quote unquote overdriven, because it's really not much input level. But the TinySA is extremely sensitive. to that. So you really need to make sure that you have a very low input level, and then the tiny SA might actually have issues. If you tell it has 50 dB of external attenuation, it's just going to add those 50 dB to any measurement it makes. And of course, the noise floor on such an inexpensive device is going to be higher to begin with. And so you might actually get into an area where you can't see as far down anymore as you should. That said, you also need to make sure that your span, which I've shown here as 22.5 megahertz, which matches with the 450 points that the Tiny SA Ultra Plus has, divided by the 100 kilohertz, and that divided again by 2. And then you have to cycle through and measure every harmonic individually. Interestingly, I actually did that comparison earlier, although I didn't put it in the slides. I have it somewhere on paper, of which you see a picture there, but I don't remember where I put the paper. The biggest deviation after manually applying the correction factors between the Rigel RSA and the Tiny SA was about 0.8 decibels at the third harmonic. That's not only not much of a difference, it's also less significance than what the standard requires. So to answer that question, yes, you can use the Tiny SA. Although one thing I'm going to add, this radio here that I used was this, whatever you want to pronounce it, Alliance HD2. Let me open it up. It's, by the way, one that a user sent in because it was so horrible, so that I could show measurements. That's the Alliance HD2. Yes, I'll hold it up in a second. This radio is extremely horrible, and because it's so horrible, it's very easy to capture the harmonics. If you have a fairly clean radio, it might quickly happen that you're going to be unable to see anything. That's a problem with the Tiny SA. Although I haven't played with it enough. Well, that was it for the presentation part. I haven't played with it enough to really make a statement about that, but yes, you can use the Tiny SA. What the exact limitations are, I can't tell you yet. One thing I don't have in the slides, but I'm going to mention, like I said, if the antenna port is inaccessible for whatever reason, then you will have to use a measurement antenna. Actually, do I have one? Of course I have one. What a question. This one here, for instance, I've shown this before multiple times. This is a biconical antenna usually used for EMC measurements. What's special about it is that there's known antenna factors for every frequency in its range, which is 30 megahertz to, like, is it 3 gigahertz or 3 gigahertz? So you can really make accurate measurements with that if you apply the antenna factors as correction factors. And if you don't have access to the antenna port, this is what you'll have to do. You'll have to set up the radio in an anechoic chamber or in an open area test site. You will have to use an antenna like that. It's nothing that you're going to do at home, and you shouldn't have to as an amateur radio operator at all. Holger says, reduce the source level by 3 decibels and check whether the spurious reduce as well. Plausible. Yes, exactly. That's the thing with the overdrive. You can just reduce the input level and see where the problems stop. Again, I don't know that precisely for the Tiny SA where the limits are. I just know that that's a problem point for it. And Roy says, a Z out from transmitters normally not 50 ohms for harmonic product. Is there a possible measurement issue? Well, that's an interesting thing that the standard really doesn't say anything about. You're absolutely right, because the measurement assumes that the output impedance of the transceiver is 50 ohms, which it usually isn't. It's mentioned as 50 ohms, but in all practicality, it's not. And the standard says, well, it doesn't say it doesn't matter. It just dictates that your artificial antenna, the dummy load, has to be 50 ohms over the entire measurement bandwidth. Will that falsify the results? Because the antennas that are on there, those cheap rubber ducky antennas, will also not have a perfect 50 ohm impedance. But this in practicality doesn't matter. Why? Because this antenna will not be a good antenna on all those harmonics. and therefore the real harmonic output will usually be lower than what you have in the conducted measurement, but the standard is actually not clear in what you do in that instance. It just dictates that and technically, if you want to play a lawyer, even if you have a transmitter that's designed for 75 ohm output impedance, for instance, I don't know why you would, but the standard dictates to use a 50 ohm measurement antenna. I'm not sure why, but that's how it is.
What is the difference there? I mean, obviously, I know that television antennas and satellite dishes use 75 ohm, as does composite video, and you're using 50 ohm on ham. Why do those two overlap?
There is many stories about that, really a lot of stories. Allegedly, the 75 ohms is the lesser attenuation for receive functions, or general lesser attenuation. The 50 ohms is better for power handling. That's kind of the story behind it. In all honesty, I personally think if you look back at the time when that was established, it's really just that some companies had to battle it out and decided that's what it's going to be. Because all the philosophy that's always applied backwards, I don't think that ever existed. I think some company said it's going to be 50 ohms and was done with it. There's some, if you look it up on Wikipedia, there's some equations that find this as the ideal middle ground between power handling and for receiving. And TV signals, which you mentioned, you only ever receive TV signals, so that's where you are, of course, more favorable to the lesser attenuation. And in amateur radio and other transmitting applications, you, of course, want the power handling or the lower loss factor. So that's true at all, but I wasn't there when that was decided.
All I remember from back in the day was building video circuits for Elector, needing a 75 ohm termination, and the only resistors were 82, and that really bust my OCD.
Oh, yes. Although in all actuality, like can I legally talk about that? Well, let's just say, imagine somebody would have possibly a few weeks ago tried to transmit on the VHF radio band, like the broadcast radio band, of course in a shielded enclosure, and only had a 75 ohm antenna, and the transmitter was 50 ohm. It doesn't matter. The SWR, the standing wave ratio between 75 ohms and 50 ohms is 1.5. That's good enough for government work, as I've been taught in the United States. So we worry sometimes too much about it, but I forgot the name of the commenter. He's, of course, right to assert that that does influence the measured harmonics. But it's the rule. It's the same with electromagnetic compatibility. We had that before. The rule dictates some impedance environment. Like, for instance, all our laptops in CISPA32 testing are tested against a normalized impedance of a wall outlet. In reality, it's straight. It could pass in an EMC lab, and in reality, it's going to annoy your neighbors. It's just how standards are. You can test for any case.
Oh, that's awesome to know. Now, I have a follow-up question, but I think we should go to the giveaway.
Yes.
We're a bit late on that, so we don't want to make the audience mad. You guys want the code word for the Tiny SA Ultra Plus ZS407 spectrum analyzer. Great piece of kit, and Ari's familiar with it, and Sebastian has one, so I think it's gotten good coverage out of this. Our Elector webinar giveaway, the URL is there, if we could have that up on screen, and the code word is quite simply EMC. So enter EMC, prove that you're not a robot, put the rest of your details, and anything else I can say there is good luck. So now we'll take some questions for this webinar. Let's look at the audience comments first. Actually, can I do my follow-up question? Speaking of 75 ohm, I have installed satellite dishes and TV antennas and had a great hobby of it, but the equipment, the test equipment, was ridiculously expensive back in the day, like a spectrum analyzer. I could not justify that for occasional use. However, I was told that if you have a splitter and you have two televisions, for example, and you're using an F connector type 75 ohm splitter, if you're not using the one outlet, you should put a 75 ohm terminator. Now, the OCD in me made me always do that, but to be honest, I never saw any difference. What sort of impact would you expect that to have?
What would I expect? Nothing at all. Exactly what you observed. In a receive setup with two TVs, there's not going to be a significant difference at all. In reality, of course, you should terminate all unused ports properly, especially on a passive splitter like that. In all actuality, nothing is going to happen unless you short that output or something like that. But even then, I wouldn't put my hand in the fire for that one, but it doesn't matter. Yes, you should, but it doesn't matter if you don't.
It might affect your cheaper equipment. I liked your analogy earlier when the cheaper and less reliable equipment could pick up the harmonics better, because sometimes being cheap can be an advantage.
It can be, yes.
Take a question from Johannes Schmidt. How is the red pitaya compared with this, besides the limit of 70 megahertz bandwidth?
I can't speak on that because I have no experience with the red pitaya. To be honest, the only contact I ever had with it is its mention in relation to Electro Talk. So I couldn't tell you, unfortunately.
Great. And a comment from Ashka M2780. Nice meeting you on a very topic on the webinar. And Holger has a tip here. Take care when performing spurious via radiation reflection. Needs to be massively reduced by measures such as in an artificial chamber.
Yes, there's really just a handful of options. It either needs to be a anechoic chamber that has absorbers that kind of look like the ones that you have behind you, just a little bit larger, or open area test sites, which is really just a fancy term of just do it on a unobstructed giant acre where the reflections can't hit you in the face.
Well, that is an interesting takeaway from that. I wouldn't have thought of that myself. What sort of frequencies are you typically working on, Sebastian? I see that S. Rupsung in Thailand is using 168 megahertz. Do you have a big ham radio antenna outside?
I don't actually do any ham radio stuff in Germany. I've done it a lot in the United States, but in Germany, honestly, I've never really developed an interest in it. So I do have antennas around me, but no amateur radio antennas. And the ones that I do have, my lawyer might be upset if I reveal what frequencies they're on. Because I mean, I can say that part, and all the amateur radio operators from Germany that are here know about that. In Germany, it's very heavily regulated what you receive. You can listen to amateur radio, and I certainly do, but even small stuff like plane spotting through ADS-B signals, it is a legal gray area, sadly, because this is kind of public information. By the way, 168 megahertz would be the old government band for police and firefighting radios over here. Now it's used for government paging.
Oh, nice. And it's good that you have the experience. I mean, in the US, you would have had more space on your property, I'm gathering. Europe, a lot of planning bureaucracy to put anything big up, right?
Yes. It's easier.
Yeah. Same in South Africa. I had, before we had KU band here, I had a 4.8 meter C-band dish, which is, I guess, around 16 foot. And what that means is I'm about 6 feet tall. So you could stand me on top of my head and you'd still need another half of me to fill up how big that dish was. I don't know how I built it myself on the roof. And then, of course, I had a whole bunch of Yagi antennas for UHF and VHF transmission. So I was already pushing the limits of someone who was living with his grandparents in a rented house. I never quite got into ham radio because those low frequency antennas get really big as well. But I saw a few in various neighborhoods. It's a pity about the space situation in Europe, because I've read a lot in magazines such as Television in the 90s from the UK, and of course a lot of Elector and others, and people were always complaining about how to get around the planning and the bureaucracy and the permissions, whereas we in the Wild West here just do what it is that we need to do.
Building obscured antennas is actually quite the genre over here because of that, and they get as odd as like inside an apartment in the walls or using the frame of the windows, and of course also outside. The Americans have the issue too. If they live in an HOA area where they can't put up antennas, then where they like use their fencing, the top of the fence, which is so isolated that you can't see it, but it works as an antenna. So this is like an art to build kind of like spy-style antennas for absolutely legal purposes, which is due to all this planning and permission stuff.
Yes, I saw someone who put a canvas, radio transparent canvas over their large C-band dish and said, it's not a satellite dish, it's a multi-purpose patio umbrella.
Right. I mean, why not?
I don't see any more questions, particularly pertaining to ham radio. So I'll just ask you, C-band. You still have an interest in C-band. Why?
It was the start of my channel, in all honesty. And when I went to the United States, obviously I've seen lots of things beforehand in radio, but I've never seen a C-band dish over here. And my very first video was a teardown of a C-band LNB. It was a DRO oscillator, a dielectric resonator, which at the time was this fascinating cube of, and it's not a cube, it's like a sphere or more toroidal, of black magic. And nowadays I know how to design those things. So I guess that is really the connection. It was the first video. I was initially interested because of that. And yes, off stage, I have convinced Brian to bring me a C-band LNB from South Africa to Europe when we meet in November, which I guess is your segue.
Yes, absolutely. I'm not going to jump into the segue. Just two more questions. Two more questions, then we'll go there. Robert wants to know, what equipment would you recommend to an electrical engineer starting out with the radio amateur hobby that doesn't break the bank?
Well, besides the obvious, which I think Robert is not asking, which would be the radio and a good antenna, it would really be a spectrum analyzer. And if you can't afford that, a tunable power meter, or at least some sort of detector and very sharply tunable filters. But a spectrum analyzer, especially if it has a tracking generator, is good for everything. If you don't have an SWR meter, you can even get impedance, at least in a scalar way, get one. And they are really not that expensive, as the Tiny SA Ultra shows. That's the one thing I would say, get it.
Great. And then being engineers, a lot of last-minute questions that just pop into mind at the moment. Gordon asked, what is the max power input for the Tiny SA? And Robert says plus 10 dBm. So I hope that's accurate, Robert, but thank you for the information. And then finally a comment. Very interesting, guys. I work on cellular networks chasing down PIM intermodulation faults.
That is a very interesting area, yeah.
I do appreciate you helping me with this segue, Sebastian. I just wanted to get in the last minute, guys. But we will be seeing you later this year, as you mentioned, because we'll be doing Electronica 2026. Elector will be. And for anyone who hasn't been, Electronica is one of the big gathering points for the electronics industry. So components, embedded systems, test and measurement, power, RF, manufacturing startups, the whole zoo. And Elector will be there always as media, as a community, and as a connector. So here are some pictures from Electronica 2024. It's a show that takes place every 2 years. So we did some news updates from Electronica in 2024. We meet engineers, companies, readers, of course, great readers, startups, people building the sort of hardware we write about all here. And there are interviews, demos, conversations on the show floor, industry updates, and usually a fair amount of, we should definitely cover that happening in real time. And here you see a couple of influences that we have. We've got Max Imagination, we've got Great Scott, we've got DIY guy Chris, and great news, Sebastian, you're planning to come through for us as part of the creator influencer side of that, which makes a lot of sense after today. Because what we've just been talking about, measurement discipline, EMC, CE, RF testing standards, it's exactly the kind of thing that separates a nice prototype from a product that survives contact with the real world. So, Sebastian, you'll be there. I'm excited to meet you in person and bring your C-band LNB, of course. What are you looking forward to seeing at Electronica, especially from the smaller hardware teams?
most importantly, I'm definitely looking forward to that C-band LNB. And after that, I can't really say what I'm looking most forward to from the teams, because that's the wrong framing for me. I'm more thinking about what am I looking forward to the most to providing to those teams or offering them assistance with. And that's exactly what you mentioned. Electromagnetic compatibility is oftentimes an afterthought. So in that fast forward area, on that space that I have available, I will show some practical things. And that's something most startups will struggle with. And it gets me excited that I can hopefully show them something and get them excited for the topic. That's really what I'm looking forward to.
Yeah, well, we'll talk about fast forward in a minute. That's a very interesting part, but I'm just curious, when you walk around an event like Electronica, what makes you stop at a stand?
That's an interesting question. I have to be honest, blinky, shiny stuff. It's the toys that you don't get to play with because they're too expensive. Sorry, I'll always remain an electronics child inside. It's the fancy blinky stuff with lots of buttons that really gets me.
Yeah, I mean, it's hard to deny, and I was surprised myself going to Electronica, and just no matter the topic, no matter the stand, if they just put up a lot of LEDs, it gets my attention, especially if they're colorful. So I guess I'm nothing more than a magpie.
Good. So we'll be visiting the same stands then. That's good. That's good to know.
Now, we were speaking about one specific part, that's Elector's presence at Electronica Fast Forward. This is where startups present, and this is the startup side of it. It's hardware and deep tech startups. If I scroll down here, stage exposure, media attention, and the chance to be seen by the right industry people. So we're especially interested in serious electronic startups to join us for RF, embedded, test and measurement, power robotics, industrial electronics, doesn't have to be RF, any kind of electronic startup. And you can visit our website to get more information about that. We'll put the link in the chat. So let's tie it back to today. Given today's topic, I'd say that if you are a startup, you're building hardware and you haven't thought properly about EMC, CE, RF behavior, or measurement yet, which Sebastian has been doing. Sebastian, you should do a startup. This is exactly the sort of ecosystem where those conversations will happen. Now, Sebastian, you'll be joining us also for startup. You'll be involved, interviewing, chatting to people. I'd ask you, do you think that startups underestimate test and measurement?
Yes, absolutely. What they particularly underestimate is testing their equipment under extreme conditions. And I don't just mean like temperature, anything like that, but as anyone knows, if you operate your prototype in the lab, users will come up with all kinds of ideas where you ask yourself, how did that even happen? And that's something that's oftentimes underestimated, testing all those extreme cases. And I put extreme in quote unquote, but you know how users are. And that's oftentimes because engineers handle the prototype different than somebody else might. I mean, the smartest thing you could do is hand it to a child and see how long it takes till it breaks, you know? And that's also in test and measurement. You design your power supply for 240 volts AC, as we have here in Germany, and the first person kills it because they're running it through a generator or inverter or something like that. And that's oftentimes underestimated.
And when I saw some of the prototypes, I found it interesting. They had finished polished products, some of these startups. Others of them also had prototypes there to show how they got there, or they were still in the prototyping phase. And I found the prototypes are interesting. Do you prefer to see final product? If you were a judge to say who should be a startup contender at Fast Forward 2026, or would you like to see the rough prototype, the under the hood sort of thing?
I would love to see the prototype, because a prototype tells me a lot about the attitude of the engineers and how well they can plan ahead. If I see a messy but well thought through prototype, I can deduct that this is going to be a great product. On the other hand, a great product will sooner or later require some revisions. And if you can't see the steps in between, you don't know how difficult that's going to be. But I love seeing raw prototypes, and ideally a few iterations from first prototype to beta version.
Awesome. Well, yeah, I kind of feel the same now. And yeah, the polished product is great. That's what you buy for your home. But it's so fascinating to see, as I said, what's under the hood. Now, if we were to ask you to judge for us the contenders, just theoretically, what would you say? Yes, these people should be at Electronica showing their product.
I don't really have
be
an
excited
answer for that.
Okay. Well, the idea was you get excited by the product. So I'm gathering something RF, and perhaps you'll find a new kind of C-band beat horn manufacturer that you can punt for fast forward.
I already see a C-band live teardown in the future, like possibly around that November.
Yes, you'll be there, and you'll have a spot, a little booth there to show off. So please, whatever you can show off, whatever will blow our minds, do that. Do a teardown. I'd love to see that. But as for fast forward, as I said, if you're watching and you're involved in a hardware or deep tech startup, or if you know one, go and have a look at Electronica Fast Forward 2026. I have put a link in the chat, so you can go straight to the link. Applications are open. So if you're a startup or you have any friends who are battling to get marketing and support and finance going for a startup, put forward your ideas to Electronica Fast Forward 2026. We are looking forward to getting a maximum of 15 carefully selected startups. We already have some, and we'd like to see your ideas coming to fruition as well. And I'd like to see your demos, especially your prototypes, on the floor. And Sebastian, at the show itself, if you see any good nerds in the wild, please send them our way. They're always welcome to contribute to Elector.
Will do.
Well, I see we are 4 minutes over. Not a problem. That brings us to the end of today's Elector webinar. Once again, I'd like to thank our old friend Sebastian Westerholt from Baltic Lab for joining us and walking us through the practical realities of spurious emissions testing. Thank you, Sebastian.
Gladly. I will see you next time literally, because it won't be long till we meet here again. So
that is great, and I look forward to it. I'm going to drop some comments on the screen. I'm not going to read them out loud because we're over the show, but I just want to give the opportunity for knowledge to flow through our channel. Thank you to everyone watching, commenting, asking questions, and taking part in the giveaway. That's quite a cool giveaway. I wouldn't mind getting one. And it's a final thanks as well to Elector Academy Pro for making today's €50 webinar available for free. So our big takeaway, I guess, for this is that a spectrum analyzer trace can look convincing, but the measurement only means something if the setup, settings, the correction factors, and the method are right. And I can't think of anyone better than Sebastian to tell us that, because he obsesses over the stuff, just as I obsess over many other things. So thank you, Sebastian. Thank you, audience. Thank you for joining us, everyone, and goodbye.
Goodbye.